Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody from the future. Today, we will continue looking into Apache Spark. Apache Spark is next generation MapReduce, if you want to put it that way. It's more generic, it's better, the jobs are more generic. And in order for this to work, we introduced YARN last week, which is a way to allocate the resources in the cluster. YARN led to not only a second version of MapReduce that threw away the job tracker and the task tracker, replacing this with an application master and containers, but also to many other applications, including Apache Spark. And so the idea, there are two ways in which this is actually more generic. The first way is that instead of having just a map phase and a reduce phase separated by shuffling, we now have a fully generic directed acyclic graph, DAG, structure in the way that the data flows. So you see that the only thing is that it cannot have directed cycles, but you see that the same intermediate data set can be used as the input of several transformations, not just one. And there are also transformations that take as input several intermediate data sets. So you can imagine that you can do things now like joins, Cartesian products, and so on, as we will see. That's the first way that it generalizes MapReduce. The second way is in what this intermediate data looks like. We saw that, I told you already last time, it's called an RDD for resilient distributed data set. Resilient because if you lose any of it, you automatically recompute it on the fly. So you can also keep it if the resources allow you in memory or on disk. Distributed because it's spread over machines. But what's important is that it's a big collection of whatever. It doesn't even need to be key value pairs. So this is more generic. It can be, I don't know, a collection of integers, a collection of JSON objects, a collection of XML elements, a collection of dates. And if you use an object-oriented programming language as the host language of Spark, if you know about polymorphism, right, in object-oriented languages, that you can build subclasses in different ways, then it means that you can even have heterogeneous collections. So you don't even need the same types all the time, just a super class that is the same. So it's just a big collection, and that collection is partitions all over the cluster. That shouldn't surprise you. I mean, until now, we saw so many things that are partitions, like the file in NGFS, they are cut in blocks. In MapReduce, the inputs is split into splits, and so on and so on, right? So an RDD can be really petabytes of data, but it's stored all over the cluster and partitions. So this is the idea, and so it doesn't have to be key value pairs. It can. You can have key value pairs if you want in an RDD, but you can also have just simple values. So now I need to tell you about the life cycle of these RDDs. How do they get created? How do they get consumed, transformed, and how are they used at the end to produce some output? In a way, it's like the life cycle of water, right? It evaporates from the seed and it rains and so on. So it's a little bit like this here. So the first thing that you need to do with RDDs is create one. How do you create one out of nothing? Well, not quite out of nothing. You actually read the data from somewhere. And that somewhere, just like MapReduce, can be from Amazon S3, can be from Azure Blob Storage, can be from the Google Cloud, can be from HDFS, if you have an HDFS cluster, can be from your local file system. I mean, you can also play with Apache Spark on your laptop. It will just spread it on your cores on your laptop, but reading from the local file system, that works as well. Can be HBase, can be a relational database, and so on and so on and so on. So there's many locations that it can come from. Plus, it can also be on the fly. You can use, so typically when you use Spark, it's just like MapReduce, you use Java or Python as an outside language to code your functions. But in that language, Java or Python, you can also generate an RDD just like that on the fly. The way you do it is that you create a list in your language, which of course will fit on the machine because that's a local list that you create in your host language. And then you use some methods to convert that list into an RDD, right? So of course, it's going to be a small RDD because you created it on the fly from a machine. But once you have an RDD, you can start applying transformations that might lead to bigger intermediate data sets, right? So it's a common way to do it, right? So locally, HDFS, S3, Azure Google Clouds, or on the fly, these are all the ways that you can create RDDs. And this is all done in some host programming language, like Java, Python, Scala, and so on. All right, so that's the first, that's the creation, right? So it's nice to create an RDD, but of course, the reason you create it is because you want to do something with it, you want to transform it. So the next thing that you can do on an RDD is a transformation. A transformation is a generalization of map and reduce. In MapReduce, you only have map and reduce. That's all you have. Of course, you can put any map function and any reduce function you want, but still, it's map and it's reduce. In Spark, you have not only these two, but you have perhaps 150 different kinds of transformations that you can apply. It's literally a Lego game, if you want. It's just playing Lego. So you have all of these building blocks, all of this restaurant menu of transformations. I'm going to show you some of them. And then you just assemble them into some DAG, picking the transformations you want, depending on your query. And then you have some complex data flow that happens in the cluster, right? So it's all taken from a restaurant menu. And finally, you have what's called an action. That's when you take an RDD, and you want to now consume it because this is the end of your query. These are your final results. So now what can you do with it? Well, if you're using Jupyter Notebooks, the simplest you can do is to just print the RDD on your screen, right? That's the simplest you can do. You just download the IDD locally to a local list. It's called materializing the RDD. So you download it locally and you print it on your screen. Of course, that only works if the RDD is small, because if the RDD is petabytes of data, you cannot download it and print it on your screen, obviously, right? But we'll see that you can just say the first 10 or something like that, so you can peek into the RDD and see it on screen. Something else you can do is take this RDD and flush it on HDFS or on S3, where you create one file for every partition. And then you will have a directory, just like the output of MapReduce. You will get a directory with maybe 1,000 or 10,000 files in there, and these files together give you the entire RDD, right? Flushed on HDFS, on S3, Azure, Google Cloud, wherever you want. Or if the RDD is small enough, you can also completely write it to your local file system, right? That also works if Spark is used locally on your machine, then it will be spit on your local file system. Okay, so creation, transformation, actually lots of transformations organized in a DAG, and then at the end, an action to use the results of your data. And of course, just like MapReduce, once you have stored your data on HDFS or S3, then you can again use that as the input of another Spark job, right? So you can also change the Spark jobs. But since the Spark jobs are actually more generic than MapReduce, you can fit much more in a single Spark job than you can fit in a single MapReduce job. All right. And of course, here, once you have created your data, maybe you aggregated massive amounts of data on petabytes. Maybe you took, I don't know, the data set generated by CERN with all these particle collisions, and you want to find your Higgs boson, and so you download the results and spot your Higgs boson on the screen. That's an example. I wanted to say something else. I can't remember. Yes, of course. Once you have output the data, one of the common things that you can do is to draw plots, scattered plots, pie charts, and so on. And then you can use other libraries, I know, like matplotlibs in Python and so on, right? So this is how then it connects with other things you can do. But of course, data visualization is out of scope for this course. There's other people who are specialized in this. All right? So creation, transformation, action. So far, so good? Okay. Now, this here is called the lineage graph, when now we know that the nodes are called RDDs. And so you see that what you have at the very top, up there, painted in green right there. This is where you create this RDD. These are all transformations where you map RDDs to RDDs, right? And then this here at the end, you can trigger an action, print it on screen, save it to HDFS, and so on. What's very important to understand is that without any action, if all you do is create an RDD and create transformations like just this, but without any action, first, this is going to be super fast. You will get an instant response. And the reason is simple, is because nothing gets actually computed at that point. If you create an RDD and transform, it only signals your intention to do this, but doesn't actually trigger any computations. The real computations start happening when you trigger an action. This is when the cluster starts orchestrating the whole data flow and compute all of the RDDs and then save on disk, right? So it's the action that triggers. So it's a lazy evaluation, if you want to call it that way. And again, just to again make this very clear, in that case, right here, yes, go ahead. Yes, exactly. If you trigger an action here, this would not even be computed. It's kind of there as a plan, but nothing happens. But then you can call an action there as well, and then it will be executed, right? So you can really reuse the RDDs and have multiple actions if you want. But it's lazy. So if you take an action here, this is not evaluated. If you only take an action here and not here, then this is not evaluated, only this, right? So lazy evaluation. Yeah.
Any step in the dark.
The action is the terminal node. So you can trigger it any way you want. You can take this and take an action here as well. That works, right? You can take any RDD and create an action or a transformation from it. So it's totally fine to also have an action here, an action there, and so on, right? I also wanted to show you here that this is an example of RDD. Awesome, answers. So is there any remaining questions? Is everybody happy with the explanations? All good? Perfect. So now we have this RDD here. That is an example of RDDs that takes two inputs, right? So I will show you later that maybe it's joining these two RDDs or computing some Cartesian product or the union or whatever. But this is an example with two inputs, and that we did not see in MapReduce, right? Here, it's an example of a fork. So basically, the same RDD is used as the input to this one and to that one, and that's fine too. Cannot do it on a quantum computer because of the no-cloning theorem, but here it's classical, so that's okay. All right. Now, in terms of languages, you can use Java, Python, Scala, and so on. Spark is actually implemented in Scala. Who heard of Scala? Many of you, right? Martin Odersky at EPFL. So it's basically running on the same virtual machine as Java, but it's a different language. That's why it's straightforward that you can also use Java to program Apache Spark. And Python also works. There is some sort of interface between the two that basically makes it work, called the streaming interface. But it works as well. You just have to expect that maybe it's going to be a bit slower if you do it in Python than directly with the native JVM, right? But it works as well. So in the Jupyter Notebook, for example. Furthermore, you can either use Spark interactively, meaning you open a Jupyter Notebook and type code and it just works. If you prefer, you can also open a shell on the command line that works just as well. It's just a less fancy version of a notebook. Or you can build an application. An application means that you create a large code base in Java or in Python that creates the RDDs, transforms them, and does things. And then what you do is that you compile it. In Java, for example, you get a jar file, and then you have a Spark submit command line executable, and you call Spark submit on the jar. It submits the application to the Spark cluster, and then everything that you have in the jar gets executed, and you can have even multiple jobs in an application, right? You can have 10 jobs, 10 actions that's going to be executed. All right? Everybody's following? Okay, that's high level for now, right? Now let me show you one. I think this is Python here, if I'm correct. I used to do it in Scala, but I'm using Python because we use that in the notebooks. So here, this is a creation. I'm creating locally a list of 2 strings. It's very, very small because that fits on a slide. So hello world, hello there, that's 2 strings. I put them in an array, in a Python list. And then this parallelize call is my creation. If I call parallelize, it's feeding that into an RDD, right? So I'm creating an RDD with these 2 strings. So it's an RDD of strings, right? You don't indicate the types in Python. In Java, you would have to indicate the types, but not in Python. So it's an RDD of strings. SC is Spark context. There's a bit of paperwork to do. So before you can actually start doing that, there's a few lines of codes that initialize the Spark context. I'm not showing them here, but it's mostly a copy paste every time. I don't really know them by heart either. I just take them and copy them whenever I need them. At the exam, you will also have them. There will be Spark at the exam like this, but again, all the initialization code will already be there in the notebook. So you don't have to know that by heart. All right. Now, what did I put in the bottom left of the screen? I put this RDD of strings, like a list of 2 strings, like a vertical table with 1 column. That's how I like to display them. But I put this dashed rectangle around. Why did I do that? Because it's lazily evaluated. This RDD of 2 strings doesn't exist anywhere. It's done on the fly. However, of course, you do have, because in that case it's on the fly, you do have the original list that, of course, is materialized here, right? But anyway, so you have now this RDD of strings. Then comes the transformation. In that case, it's a flat map transformation. And that creates another RDD that I call RDD2. This transformation here splits the strings looking at spaces, right? So I split hello world into 2 strings, hello and world, and I split hello there into 2 strings, hello and there. And since it's a flat map, I flatten everything again. So I forget what comes from where, and now I'm with 4 strings, right? Hello world, hello there. I again put the dash rectangle here because it's also lazily evaluated. This is actually not computed just yet, right? This is just on a logical level in your mind that this is what you want to do. Then comes the action, count by value. This is an action. It's documented as such. That's how I know it's an action. And then what it creates locally is a collection of key value pairs where I have all of my unique values, hello there and world, together with a count. So I have a key and a value. So you see that we also support key values just like in MapReduce, right? So the last one is a collection of key values, but not the first 2 RDDs. Do we have a question? Oh, yeah, no worries. I will let you in again. I think we have a question on Zoom, so that's good. Let me. All right, let's look at the question on Zoom then. Yeah, you open it. This looks like the logical representation of the RDD is a data frame. Is this always the case? That's an excellent question, and the answer is no, it's not always the case. In fact, here, it looks like data frame because it's highly structured, but these are not data frames. We will see data frames, probably not today, but next week. They are part of Spark. Spark supports data frames, which are better RDDs. They're going to be much faster. It's only an impression here that it looks like a data frame. But if you want to have this in mind, this visualization, I can only have 1 or 2 columns here. 1 column if it's just a collection of values, and 2 columns if it's a collection of key values. But at that point, you will not see 3 or 4 or 5 columns like any data frames like we saw them, at least not just yet, right? We'll see them next week. So your intuition is kind of correct that it's a 1 or 2 column data frame. You could put it that way. But if I want to be very precise, no, these are not actual data frames. These are really RDDs. Did it answer your question? Yep. All right. And data frames we'll see next week. You will see it's wonderful what you can do when you use data frames in Spark. Okay. Data frames are basically structured RDDs, if you want to see it this way. All right, so now I'm going to go through the overview of transformations. I'm just going down the restaurant menu, right? In the restaurant, you will see the starters, the entrees, like they call the main dish in California, the dessert, and so on and so on. So I go through them. I'll start with transformations that take one RDD and output one RDD. Here's one. It's a filter transformation. So you use it like dot filter, RDD dot filter, and so on. What does it do? It outputs a subset of the inputs, right? So some of the values in the RDD will be forwarded to the output, and some of them will not be forwarded to the output, so they are just thrown away, right? How do you decide as the user what you want to keep and not keep? Well, you need to provide a function that takes a value and says true or false. If it's true, then you're going to keep it, and if it's false, then you're going to throw it away, right? That function can be passed. Has anybody heard of lambdas? Right? A lambda is when you create a function inline in your code, right? Where you say x associated with 2x, for example, you say typically lambda x colon 2x and so on, that sort of syntax. So typically, the function here can be defined as a lambda, and then you squeeze the lambda into the filter call, and it will do the trick, right? It looks simple when you do it in your code, but you need to imagine the complexity of implementing that, because you have to realize that this function that you create in the filter transformation will need to be serialized in some way and shipped over to 1,000 machines that will all execute it locally. So it's not trivial at all to implement physically this filter transformation. But when you write the code, just put a lambda in the filter, and that does the trick. Now, that should remind you of a relational algebra operation here, right? Of course, it's not a relational table in that case, but imagine that it were, that the values are records in a table. It's an RDD of records, let's say. What relational algebra operation is this, the filter? Starts with an S. It's a selection, exactly. And in fact, we will see, because SQL will come back at some point, we'll bring back SQL on top of that. That's kind of a low level. But the filter transformation is exactly how we are going to implement a selection, so the where clause of SQL on top of this, right? So SQL will come as a higher layer on top. So this is the where clause, basically. Now, another transformation is a map. It's a bit like filter, but instead of returning true, it returns another value. So you take every value in your input and convert it or transform it to one other value in the output. Exactly one. Cannot be 0 or more, it's exactly one. So you convert every one of these values to another value, right? So this is a map transformation. You could use this to implement a projection, right? Imagine that you take a record as an input and you map it to the record, but with less fields. Imagine it's a JSON object in the input, and you output the same JSON object, but with only 2 keys, right? So map transformations can be used to implement projection. That's in the select part of the SQL. Who already sees this or visualizes this, right? So now you can imagine that if I chain a transformation that is a filter followed by a transformation that is a map, I basically implemented a select from where, if my values are records. But it's more general than that, because my values don't need to be records. They can be anything, any values. Okay? Flat map. The difference between map and flat map is that flat map can output 0, 1, or more values for each input value. And then it's flat map because then it's flattened. You forget that they were together, right? So now you just have all of these produced values in a single go. Now, the flat map here actually corresponds to the map in MapReduce. The map in MapReduce is actually a flat map. Who understands that? Right? You remember that map in MapReduce can also output 0, 1, or more values, key values. And so this is it. So if we have key values and key values, this is basically the map phase of MapReduce that we have here. Here's another one. It's a huge menu. There's really like hundreds of them in total. Another one is the distinct transformation. The distinct transformation is basically doing some duplicate elimination. It's taking all of the values, and only if it's multiple times in the input, it only outputs it once, right? Every value gets output once. So it's like a select distinct in SQL, right? Now, just observe visually, because that will have an impact on the execution, the difference between this and this. Do you see a difference? Who sees a difference in structure, right? There's spaghetti here. It's all spaghetti. So we'll see that this has an impact because this is less efficient to execute because of this going in all directions. This is more efficient because this is the sort of things that we parallelize quite well, right? But here, it's going to be a bit more work when we execute it. Here's another transformation. It's called the sample transformation. You basically, are you okay? So you execute samples. So you basically roll a dice for every value and keep it or leave it, right? So every value you keep if let's say you generate a random number between 0 and 1, and if it's higher than 0.7, then you keep it. That's an example. Then it will take 30% of your inputs. This is quite convenient if you want to work on a subset of your data that is too large and you want to start with a smaller data set, but you want to do it in a random fashion, right? Or maybe you want to do statistics and actually sample in different ways to compute, I don't know, estimators and run statistical experiments, right? There's also applications in machine learning, because I think there are researchers at ETH here who showed that in some cases, if you take a fraction of the input, you get the same results in terms of the metrics you want to achieve. All right, so this is just a few examples. There's many, many others, but these are the simplest ones. Now I'm going to show you a few transformations that take two inputs and create one output RDD. The first one is called the union. It's taking a first RDD and a second RDD, and it's just concatenating them, right? It's an opportunity, by the way, for me to say that the order here is important. It actually matters. There is an order in the values in the RDD, right? It's ordered within each partition, and the partitions are also ordered, right? So when you do the union of two transformations, you really concatenate them in this way, right? This also exists in SQL, by the way. You remember the union, you can do a select from where, union select from where. So you see, we are basically rebuilding all of the building blocks of the relational algebra, in fact, but more general because it doesn't have to be tables. Here's another one. It's an intersection transformation. So here we output all the values that are on both input RDDs. Notice again the structure here. Here, it's going to be probably easy to parallelize. Here, you will have some data traveling around in the network, right? So it's going to be more spaghetti-y. So this is very important to really realize that there are these two patterns of spaghetti, not spaghetti. All right? And another one, so you know the three when you deal with this, it's union, transformation, and subtraction. These are the big three. And the subtraction outputs all the values that appear in the RDD on the left, except if they appear on the RDD on the right. Okay, so here, these two, for example, don't get output because they appear on the right. Just an example. All right. Here's yet another one that you can, another transformation you can do with two input RDDs. It's the Cartesian product, where you have an RDD on the left, an RDD on the right. So now I just put one at the left vertical and another at the top horizontal. And we compute pairs with one value from the left, one value from the right in all possible combinations. So if I have 3 values on the left RDD and 5 values on the right RDD, then that gives me 15 pairs, right? And then I output an RDD of pairs with these values from the left and the right, right? It's tuples in Python, if you know them. By default, this is deactivated in Spark because you can imagine if you have a billion values here and a billion values there, and you end up with quintillion values, that's actually going to potentially crash your cluster, because I think even quintillion beyond what most clusters can do. So be very, very careful with the Cartesian product. You really need to pay attention to the size of your RDDs if you don't want to crash your cluster. And if you actually know what you are doing and really, really, really want to do a Cartesian product transformation, then you need to look up in the documentation the flag that allows you to reactivate Cartesian products and override the mechanism to force it. Okay. So these are a few transformations. These are the ones that are lazy, meaning that if you actually use them, no computation will actually happen. It's just creating the plan, the query plan, but without actually executing anything. So we need to look into the actions, which are the ones that trigger the computation. The first action is the collect action. It's actually the identity function, logically. It's just the same values in the output as in the input. But the difference between the two is that the input will be a distributed RDD over the cluster of machines. The output of collect will be a local Python list if you are using Python. So you see that logically an RDD and a list is the same thing on a logical level. But physically it's not, because an RDD is spread over machines. A local list is within the memory of your machine. So collect works if you know that your RDD is small enough to fit in the memory of your client, right? Otherwise, again, it's going to crash. So you really need to pay attention to what you are doing. But if it's small enough, for example, because you computed the RDD on the top as an aggregation and there are not so many keys, grouping keys, then that will work. Okay, so that's collect. Another one that always works, and that also works if you have trillions of values, is count. You have an RDD, dot count, and you get a single integer, and that's it. It pops up on your screen in your Jupyter notebook. And this is incredibly efficient because you know that the counts, we counted Pokemons, right? That can be done in parallel. Imagine all of the RDDs, the RDD distributed on 1,000 machines. Every machine just needs to count the values, and then you just do a sum of these values, and then you get your overall count. So this is extremely efficient. Even on your local laptop, it's super efficient because if you have 16 virtual cores on your laptop, you can actually do 16 counts in parallel and then add the 16 values, and that's it. So never underestimate what your laptop can do. So that's the counts. We also have counts by value. This one you already saw. It's kind of a group by if you want. But again, you need to be careful that you can only do this seriously if the number of unique values is small enough. Because if you have too many of them, then that will crash because again, you're downloading all of that to your local machine, this output. So that works if there are not too many distinct values. Take is for the case that you have an RDD of 1 trillion values and you just want to peek into a few of them, the first ones. So for this, you can use the take action. The take action is equivalent in SQL to limit for. So you see, once again, we just implement all the building blocks that are necessary to support a language like SQL. So limit for, you remember what it does? It just takes the top 4 values and doesn't return the rest. So take 4 will return the first 4 values, download them locally to your laptop, to your client, and to a local list, and then you can display the list on your screen. Okay. Top does the opposite. It's the last ones. So if I say top 4, it's going to output the last 4 values that are in there. Again, because the order actually matters. And by the way, there are transformations that sort the RDD. So you can also rearrange the order of the values of your RDD according to a specific sorting criteria, which gives you the order by of SQL. Take sample is a bit like the sample transformation. The only difference is that it downloads it. So if I take sample 4, it's giving me 4 random values from anywhere in the RDD, and again, gathered locally as a Python list. Reduce is taking all of the values and combining them with some operator that ideally should be commutative and associative and have a neutral element if you want this to work. So imagine that these are all integers and you want to compute the sum of the integers. It works. Addition is commutative, addition is associative, and it has a neutral element, 0, right? So that means that you can efficiently implement that by computing the addition on every machine that the RDD is stored on. If a machine doesn't have anything, it just outputs 0. And then you again compute the sum of these intermediate results, right? So again, this should be commutative, associative, and with a neutral element. And I think that the API even asks you for the neutral elements to give a hint to Spark. So you could also use the multiplication with 1. Mean, what is the neutral element for mean? Plus infinity, right? And for max, minus infinity. So if you're using doubles, i.e. 754, doubles or floats, then you can also have the neutral elements for the minimum and the maximum. Okay. Is there a question? Yes?
You must count the ones that are in rather than important neutral elements there.
That could actually make sense. It's probably a design decision, right, to do it in this way. I would have to think about it if there's a way that you could just mask them out. Yeah. No, you're correct. It might be a possibility. It might be that the implementation is simpler if you use a neutral element, because then you don't need to special case the empty ones. You treat them like everybody else. But that's a good point. In fact, you know, you're probably going to design, some of you, the future systems of tomorrow. And what I'm presenting to you is kind of the lessons that we've done so far and the design of how things are done. But this changes, right? Every year there's new releases, there are new ideas that come, and just because it's done that way out of experience, there are other ways to basically be doing it, right? The way it's done typically is dependent first on the experience, because we try things, we notice that some work, some do not work, some are simpler, some are less simple. Some other decisions that are made today are made because today we have this and that much memory on the machines, we have this and that much space, but maybe in 10 years, the ratio between, for example, the memory and the drives will not be the same, the ratio of the network bandwidth and the read I/O for the disk will not be the same, and that might change the decisions, right? For example, right now, there is a bit of a trend that we have less machines with more memory, right? And there's also in-memory databases that just put everything in the memory and then you manipulate in memory. And that changes the way you do things, right? Because if you have things on disk, we'll see with indices that you can use B+ trees and indices in a certain way. But if everything is in memory, you don't need B+ trees in this way anymore. You can just use in-memory structures like the good old ones you learn in theoretical computer science, right? So, so this is why, so I'm telling you, like, they ask for a neutral element and do it that way. But things might change or not be forever, or it might be that there are other systems that make different decisions. But it's a very good idea to question that, to really try to put yourself in the shoes of the engineers and ask yourself, why did they do it this way and not that way, right? And try to think about these things. Sometimes there's a reason, sometimes it's just an arbitrary decision, right? Did it answer your question?
Thank you.
Awesome. All right. We actually support pairs. As I told you, just like in MapReduce, you can have pair RDDs. And in fact, pair RDDs are so important that there are transformations just for them. Right? So an RDD of pairs is just an RDD of values where the values are pairs, right? One of the transformations on RDDs of pairs is the keys transformation. It just outputs the keys, but without the values. You just drop the values of every pair. The other one, if I correctly did it, yes, the values, that's the other one. So the values just drops the keys and only returns the values, right? So you're just taking half of each input there. Note that technically you can also do that in MapReduce, but in MapReduce still it has to be a key value. So in MapReduce you put dummy keys or dummy value when you do that. You just put a key and the value is just a null or a 0, and then you can simulate that you can actually that you have this, right? Then you have reduce by key. This in fact is the MapReduce function. That is the reduce phase of MapReduce. You basically have this collection of key values. And then you have some function that you apply to every group of key values with the same key, and that gives you some output. And of course, I can't remember that in that case it's required to be commutative and associative or not. It might not be required, But of course, as you can imagine, it affects the implementation. Knowing whether or not you can basically combine is an important aspect. All right. Group by key. This one is interesting because it's basically like the reduce by key, except that the reduce is not really a reduce, it's just the concatenation. You basically take all the values, create an array with all the values, and then you have the key. And now you have an array of values where all of the values with that key are together, right? So technically, you didn't lose any data in there. You have exactly the same data up or down, but the data at the bottom is more local. It's grouped the values together that have the same key. That's the sort of things that with SQL is not so easy to do, right? Maybe in newer versions of relational database, you kind of have a way of doing that sort of things. But normally, when you have a group by in SQL, you have aggregations that really output small quantities for each group, right? Like a sum or a count. By the way, I casually mentioned group by. Do you see that technically, when we do a map and a reduce, when we do the reduce phase with the reduce function, this corresponds to a SQL group by? Who already sees that? That this is in fact like a SQL group by. Okay, some of you. For the others, you can think about this, but this is basically on the high level that corresponds to this corresponds to a SQL group by. And this corresponds to a generalized SQL group by where you can also preserve all of the values in a group. But I'll come back to this with the language like JSONic, where we can do this very easily. I can also sort by key, right? So as the order actually matters, I can say sort by key, and here I'm using colors, so I just took the wavelength in that case. So I sorted by increasing wavelength. So you have green, then blue, then red, and you see now the same keys are together. So that's sort by key. You can also map values. So in that case, I don't change the key, but I have a mapping function that only transforms the value, and then I still output key values, but it's only the value that I actually transform. All right. So I'll stop here for today. We'll continue next week. Then I'll go, of course, into, as promised, the data frames and Spark SQL and so on. You will see how wonderful it is what they have actually built on top of the system. So it's really a better, larger, more generic MapReduce that is also more convenient to use. So before you go, just to check whether my speed is okay. Course. Today is November 8th. Here you. So just quickly checking. You know that I put every time on the website the chapters of the textbook, but there is the textbook, right? So all of that is nicely explained in the textbook, and you can just read offline, and it's just another pass on the same material. But that you can just work on at your own pace at home. Wonderful. So most of you above 80%. Some of you even understood everything. So this is great. So thank you very much. Enjoy the exercise session this afternoon and on Friday. And I will see you next week on Tuesday at 2 p.m. for the continuation of this with data frames. So see you, and thank you very much.